So let's consider the following two functions. F of x equal to x cubed minus 2x, and g of x equal to 4x minus 5. And this feels weird. At first, we just want to kind of talk about how you deal with evaluating functions. So if I want to find f of 2, I'm literally just substituting in 2 for x. So it's going to be 2 cubed minus 2 times 2, which is going to be 8 minus 4, which is 4. And just to kind of add to this, if I wanted to find, say, f of negative 3, that would be negative 3 cubed minus 2 times negative 3, which would be negative 27 plus 6, which is negative 21. What a student told me they like to do whenever they're trying to evaluate a function is they kind of write the function and put the parentheses wherever an x is. So if I want to find g of 1, I could write that as 4 times parentheses minus 5, and then plug in the 1 that is substituting in for the x. 4 minus 5 is negative 1. If I wanted to find, say, g of negative 7, that would be 4 times parentheses minus 5, and then I'd plug in negative 7 for x and get negative 28 minus 5, which is negative 33. But then things get a little bit more complicated. We want to actually compose the function. We want to find f of g of 1. And so when I look at f of g of 1, what I would really encourage you to think about is working from the inside out. So I want to look at the inside part first, which is g of 1, which we already know. We know that g of 1 from part B here, g of 1 is negative 1. So f of g of 1 is f of negative 1. Welcome. Thanks. And then f of negative 1, well, we know that f of x is x cubed minus 2x. So it's going to be parentheses cubed minus 2 times parentheses. And then we're just going to substitute in the negative 1 for x. Negative 1 cubed is negative 1. Negative 2 times negative 1 is plus 2. And we end up getting 1. And we could do this. Let's do another example. Let's look at, say, sure, g of f of, that's not exciting. Let's try g of f of 3. So the way I would really recommend doing this is, before I actually do this, I'm going to find out what f of 3 is. F of 3 is something cubed minus 2 times something. The something is the 3. 3 cubed is 27. 2 times 3 is 6. 27 minus 6 is 21. So then g of f of 3 is g of 21. And g of something is 4 times the something minus 5. So g of 21 is 4 times 21 minus 5. And that's something. It's what, 84 minus 5, which is 79. A great year. The year I was born, in case you didn't catch that. I mean, it was a pretty good year, right? Okay. Anyway, so that's how we're going to evaluate a composition of functions at a particular value, right? If you're going to find g of f of 1 or f of g of 2 or something of a number, deal with the inside part first and then apply the outer function to it. I should also mention, some people, not me, like to write something like this. There is an alternative notation. You can also write this as f circle g of 1. That means the same thing. Some people will call it fog. I don't know why. This notation is used frequently, but it's the worst notation. This is definitely the better way of writing it. It makes more sense. It's kind of showing what's happening. So I'm going to always, or almost always, write it this way, but you should be aware that this is another way of people writing this. And if you see this, if someone writes f circle g of 1, I would encourage you all to just rewrite it like that, because this is the way that just makes more sense, I think. If this makes sense to you, great, do that. But I feel like this is the sensible way of doing it. So that's the way I'm going to show it to you almost all the time. If I want to find g of f of x, on the other hand, that's going to be a function. So I'm still going to work from the inside out. I'm going to rewrite, and this is where I'm going to use some colors here because I've thought of f as this green function and g as this red function. I'm going to write this as it's going to be g of f of x, which is x cubed minus 2x. And then I know that g of x is 4x minus 5. So g of some stuff is going to be 4 times parentheses minus 5. And then I'm going to substitute in what f is. And then we can simplify if it makes sense to. Here, it probably makes sense to. I can distribute the 4 and get 4x cubed minus 8x minus 5. And that is what g of f of x would be. So I will mention, if someone asked you to find g of f of 1, I would encourage you to do it this way. We've done it already, but an alternative route to doing it would be to first find g of f of x and then just plug in 1 for x. So if I want to find, or I suppose I said g of f of what? I forget, I did g of f of 3, but you could also do g of f of 3 here and say, oh, well, g of f of 3 is going to be 4 times 3 cubed minus 8 times 3 minus 5. I don't think that's a better way of doing it, but it is a way of doing it if you wanted to see it that way. If someone was asking you to find g of f of a bunch of different numbers, like g of f of 1 and g of f of 2 and g of f of 3 and g of f of 4, then it might make sense to write this out first and then just plug in these numbers there. Right? It might be less work that. Erica.
So basically, you just use the f of x function as the x for the g of x.
Exactly. Yes. Perfect. I couldn't say it better myself. And so now we're going to do the opposite thing. We're going to find the composition f of g of x. So f of g of x. Again, I'm always working from the inside out. So I'm going to replace g of x with what it's equal to, which is 4x minus 5. And then we know that f of x is x cubed minus 2x. So f of parentheses is going to be parentheses cubed minus 2 times parentheses. Or as you said, I'm just treating the 4x minus 5 as the x. So wherever I see an x, I'm replacing it with 4x minus 5. And this, I would probably not take the time to simplify if I didn't have to. I would probably leave this as 4x minus 5 cubed minus, no, I'd probably just leave it like that, really. Could you multiply this out? Sure. Do we need to? Not really. What I want you all to see, which, okay, fine. So I'm going to multiply it out, even though it's kind of terrible. No, I really want to. I lied. I'm not going to. What I want you all to notice, though, is that these are not the same. This function and this function, definitely different. If you started multiplying this one out, the first term would be a 64x cubed, which is definitely not 4x cubed. And the last term would be something that's not negative 5. So I really, really want to stress that g of f of x and f of g of x are not generally the same. So the order of composition definitely matters. Composing something one way is different than composing it the other way. And I suppose I should say something first here. I kind of failed to mention the language here. So when we say that, when we write down f of g of x, this is the composition of f with g. No one really is ever going to say that, but in case you see it in a book somewhere, that's what they're going to say. You compose two functions. You do f of g of x, f composed with g of x. So I just said g of f of x does not equal f of g of x generally, but there is a time when they do equal each other. Specifically, if two functions are inverses. So two functions are inverse functions if f of g of x is equal to g of f of x, and they're both equal to x. So what I really like to think of when I think of this is inverse functions undo each other. F of x does something, g of x undoes it, and you get back to the x value you started with. Here is one example. F of x equal to the square root of x and g of x equal to x squared are inverses for x greater than or equal to 0. What do I mean by that? Well, really what I mean is I can show that this is true, that both f of g of x is going to be f of x squared, and then f of x is the square root of x, so f of stuff is the square root of stuff. What's the square root of x squared? It is, so it's a little dicey. I'm actually going to say a little bit more than just x here. The square root of x squared is actually the absolute value of x. If x is negative, the square root of x squared is going to be positive. The thing I always think about in the back of my mind is, I'm going to write down here, what's the square root of 5 squared? Not a trick. It's exactly 5. But what's the square root of negative 5 squared? I know you can't do this. It's the very bottom, sorry. The square root of negative 5 squared is also 5. So when you take the square root of something squared, it gives you the absolute value of the something. The absolute value of 5 is 5. The absolute value of negative 5 is also 5.
So you can say like negative 5 to negative 5 is positive 25, and then you take the square root of positive 25.
Exactly that. Square root of negative 5 squared is exactly the square root of 25, and that's exactly 5. So when you take the square root of x squared, it's not just x, it's actually the absolute value of x. But the absolute value of x is equal to x if x is positive, which they said it was right here. So it is just x in this particular problem, which is what we want, right? We are trying to get to the place where f of g of x and g of x are both equal to x. So if someone asks you to show two functions are inverses, this is how you do it. You show that both f of g of x and g of f of x are both equal to x. So let's look at g of f of x. G of f of x is g of the square root of x, which is the square root of x squared. And this is just x all the time. X had to be positive already because you can't take the square root of a negative. So the square root of x squared is just the square root of x times the square root of x, which is just x. Again, if x is greater than or equal to 0. And that's enough. We showed that both f of g of x and g of f of x are equal to x. So this shows that f of x and g of x are inverse functions. Okay. Here's another example that you might be somewhat familiar with. E to the x and the natural log of x. Or if you prefer, you could also think of 2 to the x and log base 2 of x. Those are another examples of inverse functions. And you show their inverse the same way. You're going to show their inverses by saying, okay, well, f of g of x is f of the natural log of x. And then f of some stuff is e to the stuff. Right? Instead of e to the x, it's e to the whatever's in the parentheses, which is e to the natural log of x. And what's e to the natural log of x? I know it's been a little while, but it is just x. In fact, we talked about exponential functions and logarithmic functions as inverses of each other. That's how we kind of talked about the logarithmic function in the beginning. So yeah, they do undo each other. Questions? Welcome to ask questions. Or not, it's okay. Let's look at the other way, and then we'll look at this other one as well, because I think that one's a little easier to see. G of f of x would be g of e to the x. And g of x is the natural log of x, so g of some stuff is the natural log of some stuff. And what is the natural log of e to the x? Well, we could bring the x down if you wanted to, and say it's x times the natural log of e. And then that's x times 1, which is x. So these are definitely inverse functions. Let's look at this last example, which I think is actually kind of the nicest example. Never enough room. Okay, so we'll do this one, and then we'll talk about some graphical stuff that's related to this. So are these two functions inverses? Well, before we even talk about it, I'm going to say some words about how you can kind of see that these ones are inverses. Because what these functions do is they undo each other. So f of x, what does it do? Well, it takes x, first it multiplies by 3, then we subtract 4, then we divide by 2. G of x exactly undoes that in the opposite order. So g of x takes your x and first multiplies by 2 to undo the dividing by 2. Then it adds 4 to undo the subtracting by 4. Then it divides by 3 to undo the multiplying by 3. So these functions totally undo what the other one does. It's not sufficient to show it's true for particular numbers, but I'm going to show you that f of, let's pick a nice number here, James. Sure. F of 6. If I plug in 6, what do I get? You get 3 times 6 minus 4 divided by 2, which is 18 minus 4 over 2, which is 14 over 2, which is 7. So for f of x, if you input 6, you get out 7. G of x should undo that, meaning g of 7 should equal 6, and it does. G of 7 is going to be 2 times 7 plus 4 over 3, which is 14 plus 4 over 3, which is 18 over 3, which is 6. So at least for this one example, we can see, oh yeah, g of f of 6, which is g of 7, is equal to 6. I want to stress here, that's not enough work to prove that these functions are inverses. It's good evidence that they're inverses, but to show that they're actually inverses, you have to show it's true for any x, not just for one particular value of x. So the way we actually show they're inverses is we're going to show that f of g of x is equal to x, and vice versa, that g of f of x is also equal to x. So f of g of x, this one looks kind of like a pain. It's f of 2x plus 4 over 3. And then that's going to be, so f of parentheses is, okay, it's going to be a little messy here. It's 3 times parentheses minus 4 all over 2. Now, when you simplify this, you kind of need to show a couple steps, because if you say everything cancels at once, it's a little dicey. So what cancels first? The 3's. Then I'm going to rewrite the next step as 2x plus 4 minus 4 over 2. What should I cancel next? So you could divide the whole thing by 2. You're not wrong. You could say this is equal to x plus 2 minus 2. You divide each thing by 2. But I'm going to cancel the 4's next, because that seems easy to me. And then I'm going to have 2x over 2, and then I'm going to have x, because 2 over 2 cancels. Great, f of g of x is equal to x. And we're going to see that the other way is also true. In fact, I want you all to try this one on your own. So try g of f of x, which is going to be g of 3x minus 4 over 2 which is going to be 2 times 3x minus 4 over 2 plus 4 over 3. Try that one. I know I started before you can do the rest. Well, I've got to take it. All right. Yeah, so looking like pretty close to done. So first, I'm going to cancel the 2's and get 3x minus 4 plus 4 all over 3. If you did divide, so the thing is, right here, you can't really just cancel the 3's. Because these 4's are each getting divided by 3 as well. So if you really wanted to cancel the 3's next, you could do this, although it's kind of weird. You could say it's 3x over 3 minus 4 over 3 plus 4 over 3. That's not the direction I would go. I would go in the direction of saying it's 3x minus 4 plus 4, and then the minus 4 and plus 4 cancel. That's the way I would do this. But you could also go this way and then say, oh yeah, those cancel, and 3x over 3 is just x. Oops, sorry. Paper's just a little too long. So you should be able to get back to x, assuming that they are inverses. So, and I would never ask you to show things are inverses that actually aren't inverses. So the problem says show these things are inverses. They are actually inverse functions, and you should be able to always show both that f of g of x is equal to x and that g of f of x is equal to x. You might wonder why you have to show both. And the reason is because sometimes one direction you do actually get it equal to x, and the other direction you get something kind of a little bit off. Actually, this first example is an example of if you didn't restrict the domain, you wouldn't have inverse functions. So it's a little bit tricky there. I do want to show you one more thing about all these functions, and I want to show you their graphs, because their graphs have a special property when the functions are inverses. So let me do this here. So I'll look at the first one. The first one was, and let's do some colors here. So the first one we had f of x equal to the square root of x, and g of x was equal to x squared. When I graph these, I'm just going to plot a couple points so you guys can see. So g of x equal to, so for f of x equal to the square root of x, I get the point 0, 0, 1, 1, 4, 2, and it looks like this. And for x squared, oh, I should point out, right, we were given a domain where x is greater than or equal to 0 for both of these. So usually for x squared, you would get the entire parabola, but we're going to be starting where x is greater than or equal to 0. So we're really just getting the right half of the parabola. And you might notice the points I plotted. The x and y values are interchanged. I've got 4, 2 here, I've got 2, 4 there, I've got 1, 1 here, I've got 1, 1 there, I've got 0, 0 here, I've got 0, 0, right? I think you can interchange 1, 1 and get 1, 1. Or more generally, not generally, just kind of, what we have here is that these graphs are reflections of each other across the line y equals x. And that's always true for inverse functions. Graphically, they are always mirror images of each other across the line y equals x. Let's look at a couple, the other two examples that we've talked about. So if we look at, oops, I wanted to use green, sorry. So look at f of x equal to e to the x and g of x equal to the natural log of x. We know that e to the x has a y-intercept 0, 1, has a horizontal asymptote to the left, and looks kind of like this. It's your basic exponential function shape. And the natural log of x has an x-intercept at 1, has a vertical asymptote at x equals 0, and has your basic logarithmic shape. And hopefully you all will agree, despite my not excellent graphing job here, that these are definitely mirror images of each other in the line y equals x. If you flip this red graph across that line, it's going to be the green graph and vice versa. And then you can even do it with the lines. The lines are kind of fun. Fun, okay. So for f of x equal to 3x minus 4 over 2, and g of x equal to 2x plus 4 over 3. So if I'm going to graph these lines, I'm going to graph them the easiest way I know how, which is by finding the intercepts. So for this green function, f of x, the y-intercept is going to be -2. So if I set x equal to 0, I'm going to get -2 for y. And the y-intercept, okay, if I set this equal to 0, I actually have to do some work. I set 3x minus 4 over 2 equal to 0. Multiply both sides by 2. Solve for x. Get x equal to 4/3. So there's 1, there's 2, there's 4/3 of everything. Okay. And then my other line, so the thing about graphing the other line is it should be really easy to find the intercepts because they should be just interchanged. So here for the green graph, I have a y-intercept of 0, -2. For the red graph, I'm going to have an x-intercept of -2. Hopefully you all can see, right? If we set x equal to -2, we're going to get 0 for the y value because you're going to get 2 times -2, which is -4 plus 4, which is 0. So my x-intercept here is -2. And my y-intercept for g of x, if I set x equal to 0, I'm going to get y equal to 4/3. So they've exactly interchanged the x and the y-intercepts, which happens. And these graphs, again, just like the previous ones, are mirror images of each other in the line y equals x. And they actually cross each other on the line y equals x. So when you have inverse functions, their graphs always have this nice property. And so sometimes, not me, but sometimes people might ask you to, like, they might say, here's a function, graph its inverse. And the way you graph its inverse, the way I graph its inverse, is just by interchanging all the xy coordinates. So if I know I have like these xy coordinates 0, 0, 1, 1, and 4, 2, and I want to graph the inverse, I just change all of the x's and y's. So I had 0, 0, 1, 1, and for the 4, 2, I get 2, 4. Instead of 9, 3, I get 3, 9, and so on and so on and so on. So that's an easy way to graph an inverse function if you're asked to. All right. Maybe not more interestingly, one thing that we do want to be able to do is, given a function, find its inverse. And there's a process. It's kind of like a 4-step process, but there's really only like one step that's actually hard, and the rest of the steps are really, really easy. So here's the process. We're going to first, I don't want to use f of x. I'm going to rewrite it as y equal to 4x cubed plus 1. That's my first step when I'm finding the inverse. The second step, interchange all the x's and y's. And that's actually, even though the solving part's the hard part, the interchanging part's the most important part. Because when you interchange x and y, you're literally changing the function to its inverse. You're reversing the roles of the inputs and the outputs. So we're going to write x equal to 4y cubed plus 1. And now you have a totally different inverse relationship. Here in this previous function, x could be 1 and y would be 5. In this function, x could be 5 and y would be 1. Right? They've got the points inverted. The third step is where we actually have to do some work. We're going to solve. So I should have written here, interchange in x and y. And then now we're going to solve. So I'm going to try to isolate y. So I'm going to subtract 1 from both sides. I'm going to divide both sides by 4. So x minus 1 divided by 4 equals y cubed. And then I'm going to take the cube root of both sides. So I'm going to get the cube root of x minus 1 over 4 is equal to y. That's our solving step. The last step is also kind of a nothing step. Replace y with the notation f to the negative 1 of x, which we read as f inverse of x. So step 4 is just rewrite it as f inverse of x equals the thing we found it to be, the cube root of x minus 1. Couple things about this. Kind of like the previous line one, you can kind of talk out how this one really is the inverse. This original function takes x, cubes it, then multiplies it by 4, then adds 1. And this other function first takes your input, subtracts off the 1, then divides by the 4, then takes the cube root. It's literally undoing all the things we did in the reverse order, which it needs to be so that you get them the right way. You don't have to talk it out, but I kind of like thinking about, oh, like I can really just say words and make it work. Sometimes. This next function, you can't really, at least I can't really figure out how to talk the next one out. So I will know how to undo it when there's multiple instances of x without just using the process. So let's find the inverse here. So step 1, rewrite it. I got y equal to 2x plus 3 over x minus 4. Step 2, interchange them. So every y, which there should only be one y, becomes an x, but every x, which there might be more than one of, becomes a y. So I get x equal to 2y plus 3 divided by y minus 4. This particular brand of function is usually the kind of most challenging to invert because we have to be extra careful that we isolate y and our answer doesn't have any y's in it. So the first step for solving, I'm going to multiply both sides by the denominator. So I'm going to say that y minus 4 times x equals 2y plus 3 over y minus 4 times y minus 4. You can skip writing the right-hand side like that and just say, oh yeah, James, I know that these are going to cancel. So then we have y minus 4 times x equal to 2y plus 3. And what we can't do at this stage, we can't subtract 3 and divide by 2. Because even though that'll get y by itself on the right, there will be y's in the answer. We need this to be wholly a function of just x. So to be able to isolate y's, we have to kind of group all the y's together. Before we can do that, we have to distribute this x. So x times y is xy, and x times negative 4 is minus 4x. Now I want to group all of the y things on one side and all of the not y things on the other side. It doesn't matter which side you pick. I usually try to pick sides so that there's more things that are positive than that are negative, but it doesn't really matter. I'm going to bring my y things to the left. So I'm going to have x, y minus 2y. And then I'm going to bring my not y things to the right. So I'm going to have positive 4x plus 3. The reason for doing that is so that then we can factor out a y. So I'm going to factor out a y. And when I do that, I'm left with x minus 2. It's equal to 4x plus 3. And then finally, I can divide by what's left over here. So that, or I should say, I can divide by what's multiplying y and get y equal to 4x plus 3 divided by x minus 2. And I guess I should really then take my last step, which always feels like a nothing step, and write it as f inverse of x is 4x plus 3 over x minus 2. That is the inverse function. Kind of a bit of a process. anything I want to say about that? There are lots of things I could say about that. So again, right, these functions have kind of the opposite things happening. So anything that's an X thing here is a Y thing here and vice versa. So just for example, let me ask everybody, this function here, where does it have a vertical asymptote? Where's the denominator equal to 0? It's 4, definitely. Where does this function have a horizontal asymptote? Also at 4. So vertical asymptotes for the original function correspond to horizontal asymptotes for the inverse, and vice versa.
I think I just did like different steps, but I got -4 minus 3 over -x plus 2.
It should -4x minus 3 over -x plus 2.
Oh, yeah.
That's totally right.
So,
So the only difference between what you did and what I did is you probably brought your y's to the right-hand side and your non-y's to the left-hand side, which is
Okay.
totally fine. Your answer is completely
so, like,
100%
with
correct.
the negative of the -4 and -x to cancel out, or how would that work?
So what your answer should be, if you did it the opposite way, is -4x minus 3 over -x plus 2.
Yeah.
I would leave it like that.
Well, I'm just wondering how it's equivalent.
So you can multiply the top, so you can multiply by 1.
Oh,
Multiply by 1, which is -1 over -1. The top becomes 4x plus 3, and the bottom becomes positive x minus 2.
okay.
So yeah, if your answer has like every sign opposite in the numerator and the denominator, it's the same answer. All right, let's do this last one. I want to find the inverse of f of x equal to 2 to the x minus 1 plus 3, which is an exponential function, and we expect its inverse to be a logarithmic function. Still the same steps. So I've got y equal to 2 to the x minus 1 plus 3. I'm going to interchange x and y. So if x equal to 2 to the y minus 1 plus 3. And then we're going to try and solve for y. This is where you might go a couple different ways. I'm going to show you the way I think you should do it. So I'm going to solve for y. So first I want to get the y out of the exponent here, but before I can do that, I really need to bring this 3 over. So x minus 3 equal 2 to the y minus 1. And then what's our process or our tool for getting things out of exponents? Logarithms. So I'm going to rewrite this as a logarithmic equation. What's my base? I mean, so technically you could use any base. But in this equation, if I have x minus 3 equal to 2 raised to the y minus 1, what's the most, I don't want to say natural because the natural base is e. What's the most maybe logical choice for a base? I would say 2. You could pick something else for sure and do more work, but log base 2 is the easiest base to pick because then we can say log base 2 of x minus 3 equals y minus 1. Right, I'm just using my usual log setup. If I have something like, 8 equals 2 to the third, that becomes log base 2 of 8 equal to 3. That's always the one that's in the back of my mind, like, oh yeah, that's how logs work. And then we can solve for y by adding 1 to both sides. So we get y equal to log base 2 of x minus 3 plus 1. And then I would write my inverse function. F inverse of x is equal to log base 2 of x minus 3 plus 1. Stay. So that's our process for finding inverse functions. It's 4 steps. And only one of the steps you really have to do anything. Right. So we're going to completely switch gears now and talk about something else. The difference quotient. A very important thing. So here's what I want you to know about the difference quotient. You're just finding the slope of a tangent line. Not the slope, sorry, not the slope of a tangent line, the slope of a line between 2 points. We already know the slope equation. Right? It's the difference in the y's divided by the difference in the x's. So I'm just going to remind everybody before we even get into this. In fact, I'm going to say right here. The slope between 2 points is the difference in the y's, the difference in the x's. However, we're going to give these things some other names because it's useful for us. So I'm going to call this point here A, comma, f of A. And I'm going to call this other point here B, comma, f of B. So if I want to find the slope of that line, I can use my slope equation. It's going to be, right, my first point is A, comma, f of A. My second point is B, comma, f of B. And the slope between them is, well, it's the difference in the y's divided by the difference in the x's. So it's going to be f of B minus f of A all over B minus A. The rise over the run. F of B minus f of A over B minus A. So that's how we're finding the slope of this line. Now, there's another way of writing this, which is going to be extremely useful and extremely present when you take calculus next quarter. I know I said that a lot, that when you take calculus next quarter, that's because this is pre-calculus, right? I'm trying to prepare you for the calculus you're taking next quarter. This next way of writing it is usually preferred. So I'm going to rename my points. Instead of calling that point A, I'm going to call it X. And the Y value is going to be f of X. Instead of calling this point B, I'm going to call this value X plus H. I'm going to call this value f of X plus H. So when I want to find the slope, it's still the same calculation. It's still the difference in the y's divided by the difference in the x's. Now the difference in the y's is going to be f of X plus H minus f of X. And the difference in the x's is going to be X plus H minus X. And usually people simplify this because what can I do in the denominator there? The x's can cancel. X minus X goes away and you're left with just an H. So the difference quotient that we typically think of when we talk about the difference quotient is the quantity f of X plus H minus f of X all over H. And I want to be super extra clear. F of X plus H is not f of X plus H. Those are two wildly different things. F of X plus H would take your function and shift it up by H. F of X plus H would take your function and shift it left by H. So those are very different. This one's really easy to calculate. You just take your function and you tack on an H at the end. This one's harder to calculate. You have to take your function and substitute in X plus H for every X. Okay, we're not going to get to all the examples. It's not surprising because I feel like this class always tries to, this particular section always tries to throw in too much stuff. Let's try and do these first two examples because they're not too bad. So let's simplify the difference quotient for f of X equal to 5X plus 3. So let me ask you all before I do this one. What's the slope of that line, 5X plus 3? It's 5. So if you pick any 2 points on the line, y equals 5X plus 3, you would expect the slope between them to be what? 5. The answer is going to be 5. But let's do the work to see it. So I'm going to do f of X plus H minus f of X all over H. Whenever someone says the difference quotient, this is the thing you should think of. And I'm just going to do the work. So f of X plus H, well, I'm going to take my function 5X plus 3, and I'm going to use my parentheses. I'm going to have 5 times stuff plus 3, which is going to be 5 times X plus H plus 3 minus f of x, which is 5x plus 3 all over h. Now I've made an error there. It's a pretty big deal. If I start doing this, I'm going to get the 5x's to cancel. But 3 plus 3 is 6, and that's a problem. When I simplify the difference quotient, here's what should happen every single time. Everything that does not have an h in the numerator should cancel out. So that everything that's left does have an h, so that we can factor out an h and cancel with the one h in the bottom. Because our goal, every time when we're doing the difference quotient, our ultimate goal is to get rid of that h. You are a problem that we do not like. Why is it a problem? Because later on, when you take calculus, you're talking about letting h get closer and closer to 0. We don't want to divide by 0. So that h is a problem that we want to get rid of. And to get rid of it, you need to be able to factor out h from the top. To be able to factor out h from the top, we need to make sure that we subtract all of that. So be extra careful there. You have to always be subtracting everything that f of x is. Make sure you distribute that negative sign. So then if we simplify this, it's 5x plus 5h plus 3 minus 5x minus 3 divided by h. And now things cancel that should. The 5x and the negative 5x cancel. The positive 3 and the negative 3 cancel. Bless you. We're left with 5h divided by h, and then h over h cancels. You get 5, just like we knew the answer was. Time. Okay. Yeah, we can. Let's do this last. Well, not this last example. Let's do this next example because it is good to see one more. So we're going to simplify the difference quotient here, and I do like to start off by writing f of x plus h minus f of x all over h. And if it's helpful, you might write f of x plus h down before you do this. Meaning, I might say, oh well, if this is f of x plus h, I'm literally just replacing every x with x plus h. Or as my previous student liked to do, they're going to write parentheses wherever there would have been an x, and then fill in those parentheses with x plus h. Okay, so now this is a bit of work. So I'm going to do some simplifying as I write this. X plus h squared is going to come up a lot. I encourage you to get used to remembering that x plus h quantity squared is x squared plus 2xh plus h squared. Because it's x plus h times x plus h. And that's exactly what I just said it was. So we're going to have 4 times x plus h. I didn't actually write it out like I said I was going to. Oh well, that happens. I'll distribute the 5 here. That's my f of x plus h minus all of f of x, which is 4x squared plus 5x plus 1, in parentheses so that I can distribute the minus sign all over h. Okay, let's get to work. So x plus h times x plus h is what I said before. It's x squared plus 2xh plus h squared. I still have to multiply it by 4. I got a plus 5x, a plus 5h, a plus 1. Then I have a minus 4x squared minus 5x minus 1 all over h. I can cancel something right now. What can I cancel? Definitely 5x and a negative 5x. Anything else? 1. A 1 and a negative 1. All right, good. I can't cancel the 4x squared yet because I have to distribute this 4 before I can do that. So the next step, I'm going to get 4x squared plus 8xh plus 4h squared. And then I still have a 5h and still have a minus 4x squared. Now the 4x squareds cancel. And everything that's left in the numerator has an h. That's great. I like to take the step of factoring out an h from the top. So I factor out an h, I'm left with 8x plus 4 times h to the first plus 5 all over h. And then those h, the h I factored out and the h in the bottom cancels. And I'm left with 8x plus 4h plus 5. It's perfectly fine to have other H's in your answer. The one H we want to make sure gets canceled is the one in the bottom. Every time. For sure. That's like the old, every time. So I just want to say it again as many times as I can. Whenever you're doing the difference quotient, it's always that H in the bottom that we want to cancel out.